This question is about pH. Pure water dissociates slightly. The equilibrium constant Kc, the concentration of H plus concentration of OH minus over concentration of water, the ionic product of water Kw is just got the top line of that expression. It says explain why the concentration of water is not shown in the Kw expression, and the reason for that is that the concentration of water, so not water, the concentration of water is so large in comparison to the others, it is effectively constant. So Kw is a new constant that is a combination of Kc and the concentration of water, which is a constant. Table 5 shows how Kw varies with temperature, and we can see that Kw is getting bigger, so less zeros before the numbers. Explain why the value of Kw increases as the temperature increases. So if we go back and look at this expression at the top, we can see that the dissociation is an endothermic process. And when you heat up a reaction, it shifts in the endothermic direction, and that would increase the concentration of H plus and OH minus, and therefore increase the value of Kw. So forward reaction is endothermic. Increasing temperature shifts the equilibrium to the right hand side to oppose the change and reduce temperature. This increases concentration of H plus and concentration of OH minus, so Kw increases. Give the expression for pH, so pH equals minus log to the base 10 of the hydrogen ion concentration. Calculate the pH of pure water. So in pure water, H plus equals OH minus. So Kw equals H plus squared, and H plus equals the square root of Kw. So we need to do the square root of Kw at 50. So we go back up to this table. 5.48 times 10 to the minus 14, which we can get on our calculator. And then we want to do pH is minus log to the base 10 of that number. And if we do that, and remember we always give pHs to 2 decimal places, it asks us to as well, so 6.63. It then asks us to explain why pure water is neutral even though its pH looks like it's below 7. And the reason is that H plus equals OH minus, like we said for our calculation. So we're continuing with the question. A pH meter is calibrated using a calibration graph. To create the calibration, the pH meter is used to measure the pH of separate solutions, each with a known accurate pH. And here's our calibration graph. So these are the known accurate pHs, and up the side we've got the pH meter reading. Give the true pH value when the meter reading is 5.6. So what you need to do is go along from 5.6 here to the curve, and it's just after this line here, so it's just after 5.5, but it's not at 5.6, so it's 5.55. So you can see like it's in between 5.5 and 5.6. Suggest why the pH probe is washed with distilled water between each of the calibration measurements, and that's because different solutions would contaminate each other. So we need to wash each solution off before we do the next. The calibrated pH meter is then used to measure the pH during a titration of hydrochloric acid with sodium hydroxide. Explain why the volume of sodium hydroxide added between each pH measurement is smaller as the end point of the titration is approached. So what you have to understand here is that when you're getting close, if you look at the graph, when you get into this region at around about 25, you can see that the pH changes much, much more rapidly. So we need to start adding the volume of hydroxide much more slowly, so in much smaller amounts, to avoid missing the end point of the titration. So the pH changes much more rapidly at this time, so add smaller amounts to avoid missing the end point. Table 6 shows some data about some indicators. The student plans to do a titration again using one of the indicators in Table 6 to determine the endpoint. State why all three of the indicators are suitable. So what we want to do is have a look at the ranges of these indicators. So we can see that the first one is 3.8 to 5.4, so that's from here to here. The next one, 6.8 to 8.4, so that's kind of here. And then the last one, 9.3 to 10.5, that's kind of here. And we can see that all three pH ranges of these indicators lie within the vertical part of the curve, and therefore they are suitable. To pick an indicator, its range must lie within the vertical portion of the curve, and these all do. So all three have pH range and therefore colour change. Yeah, so that's where their colour will change. Within the vertical part of the curve. (36.25 centimetres cubed of 0.2 molar sodium hydroxide are added to 25 centimetres cubed of 0.5 molar hydrochloric acid. Calculate the final pH. Now they've given us Kw in this question, which kind of indicates that this is going to have excess base at the end. But we're going to work it out with these questions because strong acid and strong base are going to neutralise each other, but there's going to be one of them more than the other, so one left over. So what we're going to do is we're going to work out the moles of NaOH by doing moles are very clever. So our volume 36.25, but we need to turn it into decimeters cubed and then times by our concentration. That comes out to be 7.25 times 10 to the minus 3 moles. Now that is also the moles of OH minus because it's a monoprotic base, so it's got one OH in it. Then we're going to do the same for the hydrochloric acid, which is a monoprotic acid, so number of moles of HCl is the same as number of moles of H+. So we do that 25 times 10 to the minus 3 times 0.15. If we do that, we get 3.75 times 10 to the minus 3. And as we suspected, there's more alkali than acid. So the number of moles of OH minus in excess left over when we subtract is giving us 3.5 times 10 to the minus 3 moles. But Kw doesn't have moles, it has concentration. So now we need to find the concentration by doing moles over volume. And now we're going to use the total volume because this excess is in the total volume of 36.25 plus 25, which is 61.25. But we want to turn that into decimeters cubed. If we do that, we get 5.71 times 10 to the minus 2. And then we're going to work out H plus from the Kw expression, which we were given earlier on, so we can just use. And it's told us it's 1 times 10 to the minus 14 at this temperature. So we're going to calculate that, type that into your calculator. And then we're going to do pH is minus the log to the base 10 of that hydrogen ion concentration that we've just worked out. And if we've done this right, we should get an alkaline pH. And remember, we always give pHs to 2 decimal places. So we're going to put that in our calculator, 12.76. And we've got our answer.